Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help demonstrate how to draw impulse momentum diagrams and apply both momentum and energy in a one-dimensional impact. So what we're looking at here, I got a picture of a pair of objects here, this red object and this green object. And in this picture, we're going to assume that the red object has a velocity of 10 meters per second to the right, and I've named that value now of VR1. And in this example, we're going to use a 1 kilogram mass and a 2 kilogram mass. I chose nice, easy examples, numbers here to work with. And what we're going to do is try to predict the two velocities, VG2 and VR2. So the velocity of the red mass, picture 2, velocity of the green mass, picture 2. So when analyzing an impact, the first thing we always want to do is draw our impulse momentum diagram. So here's what that looks like. Here's my picture 1. And what I'm going to do is draw all relevant momentum vectors in picture 1. So this red mass is moving to the right, so it's got a momentum that points this way. Momentum's a vector quantity, so it gets represented with an arrow. Magnitude of that momentum, mv. But it's the red mass, so I'm going to tack an r on there, and the v is the velocity of the red mass, picture 1. This one does not have a momentum because I'm assuming in this example that it starts from rest. So we're imagining this red object coming in here and clobbering the green object here in a one-dimensional problem. Now, my second picture. This picture here represents the system when it's in contact, when the red guy is actually in contact with the green guy. So imagine these are like maybe pool balls or something, and this is kind of a top view. The impulse between them is what's really important in this problem. The red guy is going to apply an impulse to the right on this green animal. An impulse, again, we could write it a couple different ways. I'm going to go ahead and just call it F delta T, where the F is some sort of average force. And if you're familiar with language of calculus, we could also write this as the integral of F dt over some time interval, over that really, really small time interval. Now, Newton's third law, forces always appear in pairs. The force on the green mass is to the right, and the exact same force is going to be applied to the red mass in this direction. So we're going to have another F delta T here. So again, this force is the interaction between these objects. It's the force caused by the interaction of the red object and the green object, and that force is going to be to the right on the green object, and hence this green object will start moving to the right, and that force will be to the left on the red object. And what that should do is drop that velocity vector by some amount. Third picture. So this is going to be my picture 2. So it's like starting with 1, between 1 and 2, and picture 2. And what I'm going to do now is draw momentum vectors, what I believe they're going to look like after the collision. Now, the green mass, no doubt, is going to be moving to the right. It's the only possibility here. So I'm going to go ahead and call that momentum mass of the green, velocity of the green, picture 2. The red guy I'm not really sure of. That's a mass-dependent question. The good news about dealing with vector quantities is you can typically guess a direction on a vector and the math will sort itself out. If you guess correctly, you'll get a positive value for it. If you guess incorrectly, you'll get a negative value. And that's perfectly fine. Once you get the negative value, you know that the direction is just opposite what you have assumed. I'm going to go ahead and assume that this mass keeps going. So I'm going to draw its momentum vector to the right and label it something like MR VR2. Now, it would be perfectly acceptable if you believe that momentum would point left, just draw it to the left and label it and move on. So that's how we draw an impulse momentum diagram. We draw a picture of the system with all the relevant momentum vectors shown before the impact. We draw a picture of the system when all particles are in contact. Very important to realize this picture, this is happening over like a really small time interval, like 1/100th of a second or something like that. Then we draw a picture of the system the way we believe the momentum vectors should point after impact, drawing in the appropriate vectors and labeling them. Once you have your momentum diagram drawn, now we can go ahead and start writing equations. And once you get the pictures right, the equations just about write themselves. all the momentum in this picture, which is mrvr1, plus all of the impulse in this picture. Now, we have a plus f delta t to the right and a minus f delta t to the left. Very important fact about momentum. These impulses should add to zero. Therefore, there should be no net momentum added to the system. So our original momentum plus no external impulse should therefore equal our final momentum, which I can write something like mrvr2 plus mg vg2. I think I put a B there, but that's supposed to be a G. I think in my previous example, I was using a blue mass. All right, so here's our momentum equation. Now, we have values in this example for the two masses. What we don't have is this VR2 or the VG2. So this equation has two unknowns. Don't spend much time staring at it. Just move on. Now, this is a one-dimensional example. That means we can only write one momentum equation. So we've exhausted our what we can do as far as momentum is concerned. The next thing we ask ourselves is it plausible to equate our kinetic energy in this picture to the kinetic energy in this picture? Are the kinetic energies equal? Is KE1 equal to KE2? I'm going to put a question mark there. Well, that's a complex question, and that depends on the nature of these objects here. Let me talk about the first in reality, and then if you're a physics student trying to learn how to work these problems. If you're talking about reality, if these are objects like cars or putty or things that are relatively soft, that means that when the impact is occurring, there's going to be quite a bit of material deformed. And whenever you deform material, that tends to give you temperature changes in the region where the material is deformed. Long story short, if these materials bend in any way, shape, or form, typically kinetic energy is not conserved. However, if these materials were very hard, something like pool balls, then there's very little deforming of material, and then the kinetic energy in this picture is pretty much the same as the kinetic energy in this picture. So in the real world, that's a material-dependent question. In a physics class, if you're somebody watching this video and you're trying to work on an impact problem and you can't decide this, what you're looking for is the word elastic. If you see the word elastic, that is the author saying, go ahead and equate the kinetic energies, basically. They are saying it is a collision similar to the pool ball types of collisions. So I'm going to go ahead and assume this is an elastic collision. And if we believe it's an elastic collision, then we can equate the kinetic energies, which means all the kinetic energy in this equation, well, this momentum term would have a kinetic energy that goes with it, 1/2 mr vr1 squared. This momentum would have a kinetic energy term of 1/2 mr vr2 squared. This guy would have a kinetic energy of 1/2 mg vg2 squared. And again, normally what we'd find is our initial kinetic energy is typically greater than our final kinetic energy. But if we go ahead and assume an elastic collision, we can put equality there. And here's our second equation now that we can solve for this system. So the physics of the problem is basically done, and the rest of this is algebra. I'm going to go ahead and put numerical values in here, and I went ahead and chose numerical values. That'll make the math work out relatively easy. So keeping in mind that mass R is 1 and mass G here is 2, that's going to make this equation read VR1 equals VR2 plus twice VG2. Putting 1s here, here, and a 2 here. Our kinetic energy equation is now going to read, actually, let me back up. Before I substitute, I'm going to imagine multiplying this entire equation by 2 to get rid of all the 1/2s. Then, putting a 1 right here, this term will become VR1 squared equals, and again, multiplying by 2 will cancel this 1/2, and then that's going to be a 1. So we're going to have VR2 squared plus, multiply by 2, that'll cancel this. Mass G in my example is 2 kilograms. And again, times VG2 squared. Here's my kinetic energy equation now after I've cleaned it up a little bit. Easiest way to solve these types of equations is just good old-fashioned substitution. If we solve this one for VR2, this is going to read VR2 equals VR1 minus twice VG2. And now anywhere we see a VR2, we can sub this quantity. So I'm going to go ahead and do that right there. New equation is going to read VR1 squared equals VR1 minus twice VG2, the quantity squared, plus twice VG2 squared. The next step, whoops.
I can learn to understand you much better if I can get familiar with the way you talk.
Sorry about that. Let's see, what can you do for me? You can go away. Sorry about that, folks, if that ended up in the video. So let's see. Next step is to expand this term. Now this is just like A minus B, the quantity squared. So if I go ahead and I treat this like A minus B, the quantity squared, what we're going to get is VR1 squared minus 4 times VR1 times VG2 plus 4 VG2 squared. It's just like A minus B times A minus B and FOIL it. And finally this last term plus twice VG2 squared. All right, almost done with this one, folks. Kind of a long example. I need a little more room, so I think what I'll do here is shrink this stuff down a little bit. All right, so some good news. I picked a relatively easy example, and I made this up so that it would be fairly nice to demonstrate. These guys here are just going to sum to 0. And let's see, what do we got here? Minus 4 VR1 VG2 plus, these are like terms, they can be added, and they would add to 6 VG2 squared. All right. Now, this equation here can be solved by factoring. I'm going to go ahead and factor a VG2 out of both of these terms. And then we'd be left with minus 4 VR2, forgot my 2 on that term, plus 6 VG2. This equation now has 2 solutions. This is real common when you see when you use equations that have squares in them. It introduces solutions that can't physically happen. You got to inspect these real carefully. So one solution to this is possibly could VG2 equals 0? Well, if we look at our original problem, this guy starts from rest. Then it experiences an impulse to the right. There's no possible way that this green mass is not going to be moving to the right if this is the only force acting on it. So this thing can't end up with a velocity of 0. So this VG2 equals 0, we're going to throw that one out, no way. The other solution is negative 4 VG2. Oops, got to backtrack here, folks. I think I made a little bit of a math. Let's see, this is a VR1 VG2, VR1 VG2, VR1, sorry about that, VG2, and then minus 4 VR1 plus 6 VG2 equals 0. There's the other possibility. Sorry about that, folks. Okay, we would add this term to the right and divide by 6. So VG2 is going to equal 2/3 of VR1. VR1 is 10 meters per second, so that's going to come to 6.7 meters per second, give or take, positive. And then we can get VR1 from any of our previous work. I'm going to go back and look here. I'm sorry, not VR1, VR2. VR2 we can get right here. VR2 is therefore equal to VR1, 10 meter per second, minus twice 6.7 meter per second. And I'm just going to do a quick, use my calculator here because it's late in the day and I'm tired. Minus 3.4, or give or take, minus 3.4 meter per second. Now you notice that VR2 came out negative. It's like, what does that mean? Well, remember, we guessed a direction on that vector. And that vector came out negative, and that means that the assumed direction is incorrect. Doesn't mean we've done anything wrong. In fact, we now know that VR2 is 3.4 meter per second approximately to the left. So, again, the point of this video was how to use both momentum and energy to analyze an impact. The real big ticket things are draw the momentum vectors before impact, draw a picture of the system while the contact is occurring, draw all impulses, draw momentum vectors for the system after impact, right? And that's what's known as an impulse momentum diagram. Then you can use it to write a momentum equation. The total momentum in this picture plus the total impulse in this picture should equal the total momentum in this picture. For most college physics types problems, the total impulse in this picture will usually be 0, but it doesn't have to be. And I'll go ahead and make other videos here where there is a net impulse during an impact or during one of these problems. But anyway, you write your momentum equation. If it's good enough to solve, you're done. If not, you ask yourself, is it okay to equate energies? If the answer is yes, you write out a kinetic energy equation. That'll look something like this. It's pretty typical for these things to work out to two equations, two unknowns. From this point this way is algebra. Just go through very carefully, more carefully than I did. It can be really easy to, just one little 1 turning into a 2 can be disaster if you don't catch it. So be very methodical and all will work out well. I hope this video helps demonstrate these concepts. Have a great day.